So if the UB campus is closed, I'm going to run the online class using the BB collaborator. So you should be familiar with that tool before, just in case we have the snowy day. But if the UB campus is not closed, which means that I'm going to have the lecture even though the snow or the storm or whatever. Okay. So today first, so last class we had, so 2 weeks ago, so probably you forget the most of the thing, but fortunately we didn't start anything. So from today, today we are going to a little bit and very quickly review the math book. Actually the basically is the machine learning based on a lot of the statistics as well as the linear algebra. So linear algebra and math statistics, so you learned in your middle school, high school, as well as college. As a college student, you probably learn a lot. So we will today quickly review that such a thing. Okay. Then, so I sent the 2 files. So in addition to the lecture notes, one is I think the math is not this one. This is what I learned in Korean, but I don't know how to close. How can I close? And I review this one. So I think it's a basic summary of the probability. I don't know why there's no menu. And also the linear algebra. Okay. So why don't you study for yourself? So definitely I'm going to have a couple of questions for during the midterm from the probability and the linear algebra today. So we are going to quickly review the math used in the machine learning, but mostly they are used in the data mining. So when you learn, when you study the data mining, so it requires a lot of math. It is true, but sometimes you need to prove your idea using the mathematical equation, but sometimes not. Many of the algorithms is you can prove with your experiment implementation. But I like the way of the proving with the mathematics that can actually convince, make the audience sure that your approach is correct and the best way. So in data mining, so we use a lot of probability and statistical inference, and nowadays it's getting more important. So now statistics has been used a lot so far to describe the data. So when we have the data set, what is the shape, what is the characteristic of the data? So to simplify such a problem, when I have the something number, so what is the characteristic of this? To describe this data set, we can use the statistical approach. Like for example, mean is the average is 3. Okay. Standard deviation is variance is I'm not sure it's whatever, and 2 or the root 2. So something like that. That is different from the sometimes when we have something this kind of data. Only one number is different, but the average is something different. Okay. So that is a way of using statistics so far. But nowadays, we can use such a statistical approach to predict the next step. Okay, this is a kind of the statistical inference. So we have used such a statistical inference like the regression approach. Okay, but nowadays getting more important. Pretty much you will use a lot for such a statistical approach to predict the future events, something like that. Also, linear algebra is a very traditional tool, like the optimization. If when we have the n number of attributes, okay, that n number of attributes can be represented by the linear equation. Then try to optimize. Okay, so optimization problem. That is one of the main reasons we learn the linear algebra or matrix in our math. Okay, so we will see such a, and also in data mining. So when we represent something data, for example, I have the social media data. How can you describe such a social media data? It's not like the relational database model. In relational database model, so we can describe, we can define the student data. Student can be described by student name, student ID, and the major. That's it. But what about the social media data? Social media data, a lot of information. Also sensor data. If you are using the sensor data, how many attributes? So many attributes. Sometimes the 100, 10,000, and millions of attributes can be possible. It's higher and higher, getting higher, the dimension. So at that time, not all such attributes are required when we are doing the data mining. Sometimes we need to reduce such a dimension. So that dimensionality reduction technique is also important. We will see some of the examples, such as PCA, the primary component analysis, and something like that. And definitely the optimization theory. So these are the notation that we are going to use a lot throughout the semester. So I don't have to explain, right? So this is the member element of the set. So A is a member of A, is a membership. So pretty much when you write the technical paper, so first thing you need to do is you need to define your problem. Okay, if you cannot define your problem in the paper, that doesn't make sense. So like when you learn the science in your high school, probably you learn that we need to establish a hypothesis. It's the same as a hypothesis. Okay, if you can find the problem, like whether I can predict the future trend of the social media data, Twitter or something like that. The problem is not just finding the problem, you need to define such a problem using mathematics. Okay? At that time, such a set theory can be used a lot. So you can define the A is the user, A can be user A consists of a number of users, so A1, A2, so we can define the social media data user as the set of user, something like that. So at that time we use this kind of notation a lot. And the bar is the cardinality, the how many items in the set, the B. Okay? That means when you are using this kind of notation, you should be the A and B should be defined different. Okay? And also you can see the double bar is for vector. Vector length of the vector is called the norm. Okay? For example, if you have the vector like the V1 and V2, so norm is like the distance, length. Okay? Where? Like that. I think that you learn. So if we consider vector as this one. Length is the
It's like a Euclidean distance.
oh yes, okay. And also this is a summation of discrete data, the sum of the data, and this is an integral as you have learned in your calculus. The integral is for continuous data. Okay, so mostly this is area. Okay, and this the R represent the real number, and in case it's the n to the power of n, n is n-dimensional data. Okay. Also, the word character and lowercase of the x, y, z represent the vector. Like this one, each vector has the element v1 through vn. Okay, and the uv is also vector, but mostly it's the unit vector, but not always. And the capital letter of the a, b, x bold character represent a matrix. You know the matrix is the a, b, c, d, 2 by 2 matrix, and there, so matrix is one of the way to represent the linear algebra. So it's not very complicated. And also we are going to use a lot of the function, so mapping. So y is f over x means so the input is x, and then you have the y. Okay. Sometimes such a function can be used for the object function, or it can be called as the core function, or sometimes it's called the optimization function. So the finding such a function is another important way to do. And this one, means it's a derivative. Okay? So it's a Leibniz developed such a notation, but at the same time, it's a it's more than 200 years ago. It's almost the same time, there is another mathematician who developed the exactly same idea, but different notation. But nobody remember such a thing. Only Leibniz notation are used a lot. Not a lot, only this one is used nowadays. Okay, so it's a derivative, okay, of the respect to the x. Okay, so for example, if the y equal the x squared, dy dx is
2x.
Then you remember what that is. Okay, then this is a partial derivative. Okay, sometimes the y can be represented as x1 and x2. Okay, then you can have the dy. Takes me a long time to use this notation. This is a univariate. There is only one variable, but this one can be one with respect to the x1. Okay, the partial derivative. Okay, so that is the partial derivative. That is the overall thing. Then first we are going to start from the probability. What is the probability? Chance. It's a relative chance. So for example, if I toss and do not have the coin, the chance of the head is 50%, and the other 50%. When I roll the dice, so in case it's just Q, so it's 1/6 for each number. That is the probability. That is the chance. Okay, so that probability is very important nowadays because our data set is not deterministic nowadays, which means we can just guess. We don't know. Even we cannot check each and every data. Okay, so instead we try to guess whether there might be chance. Okay, of this one or not. The how many chance. So for example, so what is the chance of the passing this course. Okay, so if I have certain evidence, so I write to the predict how many chances to how many students will pass this course one. It's just guessing. Okay, but they can be helpful for what? To prepare the discourse, and so for those who fail, so I think 90% will pass the discourse. What about the 10 students? Do I need to give up this 10 students? Probably not. I will do the same, certain adjustment, okay, to get the better passing ratio. So nowadays, many of the data are it's not deterministic. It's just probability, chance. Okay, so that is the reason nowadays such a probability has been focused a lot. Okay, so when we deal with the probability, there are two things. One is the actual experiment, which means, for example, we have the 1,000 car. Okay, the 57 of them are green. What is the chance of the green car among the 1,000 cars? You can calculate. So 57 over 1,000. Okay, that is a chance. Is it correct? I think 1.
Yeah, 1.
So 0.057. Okay, so that is the actually real experiment. However, many of the data are just guess. So either. So for example, this is the dice. We have the 6 sides of that. So what is the chance? So do we need to roll every time 1,000, 10,000? No, we don't have to. Instead, we can actually calculate such a probability of the one side of the dice as 1/6. Okay, so that is the different thing. So most of the probability is used idealize the conservative this also. Okay. And so typically the probability can be defined as the 3 components. Okay, one is the outcome. Okay, set of outcome is omega, and F is set of possible event. Okay, possible event, and the P is the probability distribution. So probability space consists of the 3 components: omega, that is the outcome, and the possible event of the E, that is the F, and the P is the probability. For example, this is the number of possible outcome. Like when you roll the dice, it's 6, something like that. And this is a possible event. For example, if we have the n number of events, so each of them can be happen or not. So which means total, if you have the n number of outcome, it can be how many combination of them? It's 2 to the power of n. For each event, it's happen, not happen, 2 cases. So next is happen, not happen, 2 cases. All combination is 2 to the power of n. So that is the possible event, and probability is for each. It's a kind of the function for each the outcome to the what is the chance of that. So that is the probability. So we will see. So this is, I think, the well-known, the axiom of the probability is definitely there's no negative, there's no bigger than 1 in the probability. So between 0 and 1. So all possible outcome is total, it should be 1. And also, there's a you can, in case of the in case of the disjoint, like this one, then you can actually have the additive, the disjoint event. You can understand. Also, discrete case is a summation. You can use the summation. Otherwise, a continuous case, you need to use the calculus, the integral. Okay. So this is an example of the discrete probability space. So we have the dice, the 6 dice. 6 sides of the dice. How many outcome omega? It's a 6. 1 through 6. Okay. Then how many possible events? It's for each happen, not happen, happen, not happen, happen, not happen, which means it's a 2 to the power of the 6. So for example, this is 1, 3, 5 are the outcome, so 3. So which means so 1 is happen, 2 is not happen, 3 is happen, 4 is not happen, 5 is happen, 6 is not happen. Okay, so it's one of 64 cases. Then the further regarding to the probability, so the outcome of the probability of each outcome is 1 over 6 because it's the same sign. Okay, and also you can add up each probability to calculate the P of 135, this event, okay, using additivity. So that is the basic of the probability. Okay, it's also another example of the discrete using the 3 coins. Okay, so using the 3 coins, so it can be 8 possible outcomes. So head, tail, something like this. So total 8 different the outcome. So all possible events happen. This one not happen. Happen, this one not happen. So you can have to the power of 8 the possible events, and also we can calculate the probability. Okay. What about the continuous case? Continuous case. So for example, height of randomly choose American male. Because it's randomly choose the American male. So this one is the height, and this one is the quotient, the probability for each of them. But this time it's not discreted. Actually, if we precise this one, it can be discreted, but this is randomly chosen, so we can guess and smoothing the other part, and we can make the continuous the probability like this one. At this time, to find the probability, this is the probability of this. Okay, so this is kind of the continuous function. So if we want to compute the probability of the less than feet, the 5 feet, 8 inch, or the something like that, you need to sum up this area. Okay, so using the calculus, the integral. Okay. And also we have just like this one. So we have the distribution of the probability along the event, this one. So it can be both the discrete and continuous, but I expect that you are familiar with such a probability density function, PDF. Okay. Another one is CDF, cumulative density function, which has the accumulated one. So it's a monotonic increase function. Then finally it's a 1. Okay, so that is the accumulative. Cumulative, the CDF, the density function, so PDF and CDF you learn in your probably high school math or the college math. Okay, so this is a continuous function. Then random variable, which is the most important part when you start your statistics. What is a random variable? It's usually x, right? P over x. Then x is a random variable. What is a random variable?
Just chosen.
It's not h.
It's
not.
It's a function.
It's kind of function. That's a common mistake. So many people believe the random variable is just an event. That is an event. Okay. That is outcome. So but random variable is kind of function. From what? From event to the probability. Okay, so as you can see, random variable is a function that associates number x with the outcome. Okay, then it's the probability. It's kind of the function probability function. That is a random variable. That is a variable that you are going to use. If you adopt such a statistical approach, you need to define what is a random variable in your case. Like for example, nowadays many students are using the Bayesian rule, Bayesian approach. What is a random variable over here? So what is a conditional variable? Something like that. At the time, you need to define such a random variable of the X. For example, X is the social media user. Okay. Then another variable is the profile. So given profile, what is the probability of the user, like the gender classification? We can use such approach for the gender classification or something influential user. So like based on that. So we will see such a Bayesian rule later. But at the time, first you should be able to define random variable. So that is the most important part in the the probability. Okay. So for example, there is an example: X number of head in 3 flips of coin. So X is defined as number of head. Okay. How many different? 0. Okay. And 1 head, 2 head, 3 head. So X variable, random variable X is 0, 1, 2, 3. For 0, what is the probability of the no head? How many different cases?
8.
8 different cases. Then how many times no head? Which means
1/8.
the T, right? Tail, tail, tail. How many? The 1. 1/8. That is the probability function. So for x equals 0, probability of x equals 0 is 1/8. Okay? If this one is 1, how many? 3 times, right? HTT, THT, TTH, 3 out of 8. Okay? So that is 3 out of 8. So 2 is also 3 out of 8, and x equals 3 is 1/8. That is a random variable. So don't be confused with such a the possible outcome with the random variable. We are going to use all of the statistical approach use such a random variable. Another example is, let's see the other. Then these are the univariate. The variation is kind of variable. So how many variables here? So this is just x. How many head? Only one variable. But sometimes we can have the multiple variable x, y in the probability. That is called the multivariate probability distribution. When you read the technical paper, so you probably see the sum of the approaches, the multivariate, whatever, something like that. At that time, that means it considers not only just one, the random variable, it considers the many random variable. Okay? Sometimes it's called the joint, the probability, because it considers the variables, many conditions. So, for example, the two processes whose outcome are represented by random x and y, probably that process x has outcome x and process y has outcome y, which means x equals x, y equals y. The probability of this one is a joint probability because that considers two variables. So for example, this one. So x, one of the variables is the model type, like the sedan, minivan, SUV, and sport. And another variable is the manufacturer. European car is the manufacturer, location of the manufacturer. Let's say the European, Asian, and American. Okay, so what is the probability? Joint probability. The minivan also produced, manufactured in Europe, so x and y. That is this one. That is 0.14, something like that. Okay, that is the joint probability in multivariate distribution. You can see it's a 2-dimensional. Okay, it can be 3-dimensional, 4-dimensional also. And in the multivariate the probability distribution, and we are going to, so this is just the marginal, so which means marginal is like this example. So what is the probability of the miniband? Okay, that consider all the manufacturer, then we can add up. Then that is 1.3, the probability. But more important thing is the conditional probability in case that condition can be represented by the bar like this. In case of when it's a given condition, y equal 1, okay, certain specific value, what is the probability of x? Not all x, but in case of 1. Okay, that is can be represented by this one. Also, it can be extended to the Bayesian rule. Bayes' rule is such a conditional probability will be represented by the Bayes. To prove that, so we will see. So for example, such a conditional probability, even the miniband. Among the miniband, what is the probability of the manufacturer in European countries? So we will consider only the miniband. Okay, this is 1. Okay, among them, the European car is this much. That is not just 1.14, but 0.14 among these three. So that is the 44%. Okay, that is a conditional probability that is used a lot nowadays. Most of the approach use such a Bayesian, the conditional probability. At the time, the different thing is whether we are going to consider training or something other. So we will see. Okay. In case of continuous, so we can send some Gaussian mixture. When we are saying the Gaussian mixture, each variable can be represented by Gaussian distribution. What is the Gaussian distribution? It's a normal distribution, but normal distribution it has the bell shape. Okay, this is the Gaussian distribution. It has the mean value and standard deviation. So using the mean value and the standard deviation, we can represent such a distribution, that is the Gaussian distribution. The normal distribution is adjust to the 0, the average mean value. Okay, so Gaussian distribution, you may realize when you read such a data mining book or the machine learning or the many of the approaches, they use Gaussian the distribution a lot. Why? Because it's popular. Because of the
as the data size grows, that their values tend to be normalized.
Yeah. That is called central limit theorem. So because of the central limit theorem, so it's really it is central limit theorem. So central limit theorem means, so when we have the certain amount of the size of the data, it's usually more than 30. Okay, when you have such amount of the data, such any kind of data set, if you rearrange the outcome, the random variable in order, that tends to the Gaussian distribution. So think about so in nature, there might be something happen if you, any kind of the frequency, any kind of event, if there might be some frequently happen, right? So frequently happen and rarely happen. Anything, right? If you rearrange such an event, that's usual, right? That is actually central limit theorem. Okay? Central limit theorem means any kind of distribution, if you reorder random variable, it tends to, because some of the the event frequently happen, that will be in the middle, and the other are the side as the outlier. So that is the central limit theorem. That is the reason. So we can use the Gaussian distribution as a model of our data. Then the one of the benefits of using such a Gaussian distribution is it can be represented by mean and the variance. Only two parameters. We can find only two parameters. Then we can predict. That is the benefit of using the Gaussian. And sometimes it can have the multi-Gaussian distribution. That is the Gaussian, the mixture model. Okay, this usually happens, but number of the number of the average and number of variance. That's the only thing we can find. So it's easy to find. That is the reason Gaussian model used. So this is an example of the continuous multivariate. So in case of the Gaussian mixture. So there are three forms you can see. So these three can be considered sometimes outlier, or sometimes the characteristic of the data set. So once we know this one, then we can use this for prediction or the analysis. In statistics, we have the expected value is kind of weighted probability. So for example, if I toss the coin, in case of a head, I will give the $10. Okay, the tail and head, you need to give me the $20, something like that. Are you going to toss the coin? Probably not. Why? Because expected value is minus for you, right? So that is the expected value, weighted by the value, okay? So, and then one of the example of such a expected value is the average. Average is kind of the very popular, the expected value for kind of the probability weighted average value. Okay, and this is one of the way to describe such a data set or distribution. So one of the example of the central tendency. I cannot remember exactly because we try to find the center of this. The central, one of the example of the central tendency, the value. So example of such expected value. For this is the example of the two outcomes, the base curve and not base curve. Then we can compute. The expected value is minus. We do not go for this one. So think about the casino. Casino usually have the expected value. It's a minus, little bit less. The chance of the winning the game in the casino is usually 48%. Okay, little bit less than the 50% always. So which means that if you keep the betting in the casino, you may lose. But because of that margin, you have a chance. That is the reason that you keep trying. In case of the continuous, so we can also calculate the expected value. So this is the distribution, and this is the value compensation. And if we multiply the curve, then you will have such the expected value. And the most common, the form of such expected value is one of them is a mean. Okay, so the center of the distribution is center of distribution. One of the parameters to describe the distribution. Another one is the mean is such a way mu. Usually we use the Greek letter mu to represent our mean. The number of a sum of the outcome divided by number of the value and divided by number. Okay? Also, another one is a variance. Variance are usually good parameter to describe how much spread out. Okay, here, you know how to compute the variance, how much far from the average, then add up, then divide by the number of items, like this way. Okay. So n should be bigger than 1. Okay, in case 1, it doesn't make sense. And also we have the covariance in case of the multivariated. So we have the x and y, how much they are not correlated. Correlation, we will discuss the correlation later, is kind of the it's normalized. Okay, but covariance is it shows the relationship between one, the variable, and another variable. So for example, in this case, it's not the related covariance. Okay, but this one is the highly covariance, which means they are related. So we can use such a covariance in our data mining also later. Okay, so at this time, so when we have the x and y variable, the random variable, so we got this graph. So we have a very high covariance between x and y. Do you need to keep both of them or throw away one of them? You don't have to keep both of them. Why? Because if we know the x, we can estimate the y, which means they are the same tendency. Which means x and y, they are the same variable. So we don't have to keep both of them. Instead, we can use one of them. Also, using one of them, we can credit the other. However, on the other hand, this one, it's not, we cannot find any covariance. So that is a covariance, and the correlation is a normalized one. So divided by the product of the variance x and y. Okay. So such a covariance matrix, sometimes we can use a matrix in case we have the n number of and the n number of the variable. So we try to find all the covariance between n and using matrix. So like the one, because it's the first, they are the same, and the find. This value, using this value, we can sometimes find the dominant feature. Okay, it's kind of the PCA, principal compound analysis. Also, we try to reduce the dimension using such a covariance matrix. Then that covariance matrix will be very, very useful further in data mining. And from now on, we will see some basic rules used in the probability. It's a complementary rule. So A, not A. By adding the A and not A, it will be 1. It's an obvious thing. Okay. And from now on, we will get close to the Bayesian, the conditional probability. So what about the product rule? Product rule is probability of A and B. So that is this part, right? That is the conditional probability of A given B, which means what is the probability of A among B, right? That is, and to get this probability, we need to product PA bar B times the PBA. Okay, that is the Bayesian rule. Okay, so for example, that is the product rule. Okay, so for example, probability that a man has a white hair. White hair is one event. Okay, let's say that is the A. Okay, and over age is another variable. So color of hair is one variable, and the age is another variable. So P of B. Okay, so what is the probability of 65? That is 18%. 0.18. Okay, then function. How can we do that? For a given the b, in case of the 65, to here, the white hair is a 0.78, which means from here, so among the 65 to be a white hair, chance of the white hair is 78, okay, 0.78. So the math probability that man has white hair and also the 65 can be calculated by the product with the POB. POB is the, what is, that makes sense, right? So this is a chance of the conditional probability in case of B. Okay, in case of this age, what is the probability? But this is not the general, the probability is a conditional probability among 65. So we need to times what is the probability to be a 65. That is 0.18. So we need to times product. Then we can have the 0.14. That is the probability among all the people. What is the probability of being the white hair with the 65? It's a product rule. It's obvious, right? And we can use such a product rule for total probability. Total probability is this is the total probability, and this is AB. It's A, not B, and not there is a B, not A. These are the not A, not B. So probability of A is AB plus this part complement of the B. Okay. And also, if they A and B are independent, independent means no common. Okay, they are independent case. Independent case. So given B doesn't affect anything, so it's the same as P of A, probability of A. Because A and B are independent, B doesn't affect anything. Okay? And similarly, so we can from the product rule, so we can have the P A and B is the same as the P of A times the P of B. Okay? What is the dependent? Dependent case is it has a covariance. Okay? Independent case, not many. You can realize the most of data. So for example, so if our data set is the user profile, each user of the Facebook has something age and hobby or location and the occupation and so on. Then sometimes your age, using age can affect something other profile, like the hobby. So probably the 70, 80 years old people does not like the what's that, the lab or the something extreme sport. Okay, they are related. Using that covariance relation, we can actually predict. We try to use such a correlation. So this is an independent case. Okay. So many of the cases are the dependent case, not independent. But it is true. Sometimes we can assume the data set are independent. The x and y variable are independent. Then we can process. Why? Because independence case is easy. Okay? And even though there is a slightly dependent, so we ignore such a case. Okay? So using such an idea, we can actually derive the Gaussian later. Okay? So independence case, even though we roll a dice, so I think I gave the examples of the roulette game in casino last time. Okay, even though you can see a lot of red, the light in the casino. Have you been in the casino? If you go to the casino, you can. The only game I can play is a roulette because it's simple. Right? You can just bet odd number or the even number or the sometimes the red or the green. Okay, See, it's very simple. So, which means if you can see a lot of the odd number here, there might be higher chance for even number next time, which is not true because it's independent. So, which means it doesn't affect the current occurrence was not impacted by the previous one. Even though 100 times the odd number, when I toss the coin 100 times straight, that might be possible 2 to the power of the 100 chance, right? So over 1 over 2. So even though 100 times straight back to back the odd number, what about the next one? Is it higher chance to be an even number? No. It's still 50%. Okay, that is the independence. So that is the independence case. So flip the coin. So roulette game is the independence. So do not believe a lot. So the bar, you can see the bar, the history of the last 20 tours, something like that. Okay. And dependence, the height and weight. It's a dependent. There maybe we can find the covariance for that. So, and